Okay, so my name is Dwayne Wessels, and this is some work that I've done in conjunction and on behalf of CADA. We got permission to take some TCP dump traces from one of the root name servers, and this talk is sort of all about characterizing that traffic and analyzing it. And it's pretty similar to a talk that Evie gave probably 4 or so NANOGs ago, I believe. So here's the one-page tutorial on what the root name servers are. They are 13 starting points for locating anything in the DNS. They have names A through M. Each one of them handles on the order of 100 million queries per day. There's a web page at CADA that has some statistics to back that up for about 5 or 6 of the root name servers. The interesting thing about this is most of the answers that the root name servers give out have very large TTLs on the order of days or a week, and it's odd that we would see this many queries there. So why is this happening? As I mentioned, this talk comes from the F root server. It's 24 hours of a TCP dump. I logged 152 million queries from 382,000 source addresses. 220 of the 220 busiest source addresses generated half of all of the queries on this day. Here's a quick breakdown of the types of queries received. Not surprisingly, the most popular is A queries, IPv4 address lookups, and then PTR queries, and so on. One of the things I looked at was whether or not the recursion desired bit was set in each query. So here there are 3.4 million queries with this bit set. Most likely these come directly from stub resolvers. These are sort of stupid resolvers that don't have enough smarts to follow all of the referrals to resolve names themselves. So it's a little bit interesting to me that these stub resolvers are talking or trying to talk directly to the root servers instead of going through a local name server. Now I've got a few pages on some of the busier clients logged this day. All of the IP address information has sort of been sanitized to protect the guilty. And let's see. So the busiest source this day generated 3 million queries on its own, which is 2% of the total. This IP address did not actually resolve to something.mil. Rather, the whois information indicated that it's in a network that belongs to the U.S. military. I couldn't ping or in any way contact this address, and I went to the U of O route view server, and it told me that this network is not in the routing table, so doubly interesting. And as you can see the examples here, more than 75% of the queries from this source were from a single, or for a single non-existent name, this BURRBXR1 thingy. Perhaps somebody knows what this might possibly be. I don't know. This is also that same source. This is a plot of the first 1,000 queries over time, and you can see that it's very bursty. They come in inconsistent bursts, and looks like maybe 50 or so queries at a time, and then it's quiet for a while, and then you get another burst. I suppose that could be due to queuing or something else. The second busiest source came from a company that offers domain name registration services. 2.5 million queries. Of those, 10% are for 2 names in that company's own domain. Even worse, almost 60% are for the root servers themselves. And you can see by this table down here that for every name it looks like they're requesting an IPv4 address and 2 types of IPv6 addresses. So as if that's not bad enough, this particular company was responsible for 30 sources in the trace file, and altogether they comprise 15% of the traffic received at the root name server at f.root. Similar statistics as before. About 60% were for the root servers themselves and 15% for names in this company's own domain. This company actually answered our emails eventually as to what might be going on, and it turns out that they were blocking incoming messages from probably the world. They were allowing their queries to leave their network, but not allowing them back in. So the number 3 busiest source was apparently a customer of some DSL service provider. 2 million queries. Almost all of those were pointer queries, and almost all of those were for a single IP address in the inatter.arpa zone. This source exhibits what I call the query ID less than 16K syndrome. The DNS message has a query ID field, and the range is 0 to 65K. But we see quite a lot of the busy sources in this trace only use 0 to 16K, and they have sort of a pretty pattern, which is this pattern, although this comes from a different source. So it looks like they're using probably a set of incrementing counters or something for their query IDs. We haven't yet been able to determine exactly what software this is, and if anybody knows, I would love to talk to you. Again, we see this in a lot of the busiest sources, so it seems like either they have a bug in their software or people who use this software often misconfigure it. Number 22 was sort of interesting because all of their queries were for localhost, and each query was repeated 8 to 12 times consecutively. Sorry, I don't have enough space on the slide to show all of those, but you can see a few of those here. This one also has this strange query ID less than 16K syndrome. I sort of ran across this one randomly. There was a pair of sources that send identical queries from 2 different IP addresses in 2 different subnets to the root server. I really can't explain why this would be going on unless they have some device that's port mirroring or duplicating their packets or something like that. But you'll notice that the timestamps are very close. They're on the order of a millisecond apart. The query ID field is the same. The thing that it's querying for is the same. These are apparently identical packets. Okay, so the next section that I have to talk about is my goal was to take this trace of 152 million queries and classify each query into one of 9 categories. And these categories that I present here are in the order that my software looks for them. So, for example, the first category is does this query have an unused query class? The IANA and the software defines about 5 known query classes, and anything not in one of those classes gets logged as unused. Here's some examples as reported by TCPDump. Not exactly sure what might be going on here. This could be bugs, or this could be people sending garbage packets to the root name server, perhaps. Who knows? The next category is a name server or a query that requests the IP address of an IP address. This is something that Evie Namath identified in her talk, and reportedly got someone at Microsoft to admit that it was a bug in their resolver software and that they had fixed it for Service Pack 2. We're still seeing some of it. And by the way, at the end of this, I have the breakdown of the percentages for all these different categories. Next is an unknown top-level domain. So I took the list of currently known TLDs, and anything not matching that list is counted into this category. Here's a few examples. There's a mixture of some of these more strange names like BRZTU-IC4, and some non-printable characters, and MSDCS.msap.local, and so on. The next category is non-printable content in the query name. The first one here has a control A mysteriously inserted. The second one comes from somewhere in Asia. They're apparently using their own character set for their host names. This one is the appearance of RFC 1918 addresses in pointer queries. And as we've heard more than once today and before, these addresses should not really escape out into the public internet. However, they still do. There's a few interesting examples there. So all the previous queries classes were sort of easy to categorize. Now I'm getting into the ones that are a little bit harder. A repeated query is one where a lot of things have to be the same. The query ID has to be the same, the query type, the class, and the name. In my code, there's no restriction on the time constraint, so if a query is repeated in this way, separated by a millisecond or a day, it doesn't matter, it's still counted as a repeated query. Here's some examples. There's a source requesting equinox.ie, and actually a lot of sources repeating queries for things in inatter.arpa. Repeated key names is similar, although it's a little bit less strict. It doesn't have to have the same query ID, but the type, class, and the name have to be the same. And again, there's no time constraints. Here's another example. I believe this is the last category, and the one that I had the hardest time sort of defining and implementing. I wanted to see if I could tell if DNS clients or the name servers were not caching name server referrals. So for example, if I ask for a.foo.com, I should get back a referral to go somewhere else to find out about foo.com, and I shouldn't later ask the root name server for b.foo.com. That happens anyway, and there's an example here in the DNS2go.com domain where somebody's asking for a lot of different host names in that zone. Anything that didn't match one of those other categories is classified as a legitimate query. So if you haven't been paying attention until now, this is the time to look up from your laptops, because this is the best slide in the talk. According to my analysis, only 2% of the queries arriving at the name server were legitimate. You can see that the most popular category was repeated query names, almost 45%, and repeated queries contribute another 25%. Unknown top-level domains is just sort of big. Still see a lot of address lookups for IP addresses, and so on. The unused query class and RFC 1918 turned out to be sort of not as significant as the others. Here's a graphical representation of the same data. This is a little bit complicated, but for each category I ranked the counts and plotted them here. I don't know if you can differentiate some of the colors, but towards the bottom there's a green line which starts very low and goes out very far past 100,000. That's the line for the legitimate queries. That means, for example, that the source that sent the most legitimate queries sent looks like about 2,500 legitimate queries. That was the busiest source sending legitimate queries. And conversely, ones sending out repeat queries were sending, on the order of 2 million repeated queries from an individual source. So this table compares my analysis to the analysis done by Evie and others last year. In the previous study, the percentage of repeated queries was higher, as were the percent of unknown top-level domains, as were address lookups for addresses and RFC 1918 pointer queries. The previous study, the longest trace was only 2 hours, however, so that may have affected this comparison. And also, in the previous study, they were logging queries received from RFC 1918 addresses, whereas in my data, those queries had been filtered out before reaching the root name server. This plot shows sort of a histogram of the time between repeated queries. And again, this is the category of the repeated query, not the repeated key name. Remember, the repeated query has to have the query ID matching. And as you can see, about half of all the repeated queries happen less than 100 seconds. The 100 got cut off there in the end. There's sort of an interesting pattern in the blue spikes there. Those are separated by 4 seconds each. I believe that the most popular, the tallest spike is 64 seconds, and then 68 seconds, and so on. And this is the same plot for repeated query names, and you see a very strong spike at 4 seconds, which and indeed spikes at whole second intervals, which is sort of interesting. This is shifted down quite a bit. 4 seconds is about the point where is about the median for this data. Half of all queries, repeated queries, come within 4 seconds. Here's a table of popular query names received. Perhaps not too surprisingly, the most popular query was for the root zone itself, dot. Then comes this EURRBXR1 from that single source, and then localhost, and so on. Rootservers.net names are very popular. There's some other ones that are sort of strange. They're probably from single broken sources, whereas something like localhost comes from a lot of different sources. One of my favorites is WPAD, which stands for Web Proxy Auto Discovery. This is a protocol put forth by Microsoft and Inktomi for browsers to locate their caching proxies, and they're supposed to append or prepend WPAD to their own domain name, like wpadinfo.com, but instead, I guess if the host doesn't have a domain name, it just sends a query for WPAD. This is a similar table. This is just the top-level domains that were of the query names. Here I was sort of interested to see if there's any, indication of what software might be sending queries. For example, you can see. Well, I can't explain Elvis, but you can see query names for admin. MSFT is sort of interesting. Localhost, local domain, and .lam. Pardon me? Workgroup, yeah. Since this is a TCP dump trace, I can take the IP TTL field and sort of use that to do a crude operating system fingerprinting. And that's what this graph shows. This is a histogram of the TTL values from the trace. And surfing around the web and sort of using some heuristics, I broadly categorizing that Linux and BSD systems start with TTL of 64, Windows starts with a TTL of 128, and Solaris and maybe Cisco equipment starts with 255. And there's two lines here. The red line is all of the sources in the trace file, and the blue line is the busiest sources. It's actually the 220 busiest sources that I mentioned at the beginning, minus the what I consider the anomaly of the 28 name servers from this single domain name registration company. This is sort of the same data in a table form. It looks like, again, except for the main registration company, almost 60% of the busiest sources appear to be running Windows, or something that starts with 128 is their TTL. How much time do I have? Oh my gosh, okay. So here's a few random thoughts that I've had while working on this. The biggest question is what can be causing this? Not too surprisingly, and as we found out in the case of one of the busy sources, firewalls and packet filters that block DNS answers confuse name servers. They repeat their queries again and again, eventually hoping that someone will answer them. Incorrect name server configuration is a problem. That doesn't show up as much in particular the RFC 1918 problem doesn't show up as much here as it does in some of the other work that Kata is doing, and what Paul talked about this afternoon with the AS112 project, which serves those zones, like 10.inadder.arpa. Retransmission appears to be a problem. Either people implementing the software don't understand it, just ignore the protocol and suggestions for retransmission, and we might have other mysterious implementation bugs along the lines of the address for an address query, or a query. So when I first looked at that table that showed that 70% of all the queries were repeats, I was hoping, if we just eliminate all these repeats, then this will solve our problem. But it doesn't look like that's actually going to happen, because a lot of the queries actually have reasonable delays between their retransmissions. 4 seconds was the most popular in that one plot, and I counted that 16% have retransmission delay of less than 2 seconds. So technically, they're sort of in violation of the recommendation of the RFC. Furthermore, just increasing these delays doesn't mean that these queries are going to go away. They're just going to come later, perhaps. So there's some wild and crazy ideas for things we might be able to do to reduce the load on the name server. When a name server doesn't get any answers back, perhaps because of a firewall, it could stop, or it could slow down its rate of queries to the name server. It could try to complain to syslog or somewhere to get an administrator's attention, or it could exit to get the administrator's attention and just stop functioning altogether. Name servers could somehow learn which top-level domains are valid and which ones are not, and they could not forward queries for unknown top-level domains. These last two suggestions are pretty minor because they didn't contribute a lot to the load on the name server, but they could also not forward non-ASCII characters or unused types and classes. Perhaps name server software could install the RFC 1918 zones by default. Perhaps people could better test their software with QA tools. One of the things that we tried was to contact the abusers and ask them, do you know this is going on? Or can you explain to us why this is happening? It's not all that difficult to find contact information for a network or an IP address, but getting people to reply is another matter. A lot of times they just ignore you, or the right person would never get your message. Another thought we had is to post sort of weekly abuse reports along the lines of the CITO report, which I believe is not being done anymore. So I've written some software that you can download and run on your own systems and networks to sort of look at the DNS traffic on your own. Hopefully, at least a few people will do that and maybe be able to identify cases where their own servers are misconfigured or their clients are misbehaving or something like that. This software I called DNS Top, and it displays tables of various statistics of the packets that it sees. You can also replay a saved TCP dump session, and you can download it at that URL. I'm actually going to try to do a live demo of it right now if you're ready for that. So it was already running, and I just sort of reset it here. This is running on a smallish exchange point, and the IP addresses have been anonymized to keep everybody happy. Almost everybody happy, except me, I guess. So here you can see there's one source that's responsible for something like 20% of the queries. That seems a bit excessive. Of course, at this level, we don't know exactly what those queries are, and this software wouldn't tell you. You would have to do a TCP dump manual or something like that. You could display the destinations. So something like 18% of the queries are going to a single name server. That could be perfectly normal. That could be a local caching name server that should be getting out of these queries. You can display what types of queries are coming through. Again, this is similar to what I showed before. A queries are the most popular, and so on. You can look at the top-level domains that are being queried, and most of those look normal, except there's a couple of strange ones. They don't contribute much. And optionally, you can also look at the second-level domain data. So if anybody is interested in that, please download it and try it. It's out there for you to use. So here's a few people I wish to thank. These organizations operate root name servers, and they've given, excuse me, they've given Kata access to do some tracing and whatnot. These are the two organizations that answered to our email messages that we sent out, and this is the organization that gave us the money to do this study. And here's some URLs for more information, and I'm ready for an obvious question, I think.
It's an easy question, preceded by a comment, which is that you've been doing good work sort of examining the refuse from a root canal. At least that's what it appears, according to Martin. So the question is, when you're looking at the repeaters, the reason that you're not just catching a TTL expiry is because the query ID is the same? Or help me understand that. If you're not looking at, if it could be a second or it could be a day, and the TTL could be an hour, how do you know that you're not just catching TTL expire next request, and someone could like make the query ID a hash of, something which would be consistent with the
right
URL or something? Or, I mean,
one assumption that I've made, which I wish I could be more confident about its truth, is that any authoritative answer from the root name server has a TTL longer than a day.
Okay.
So if the client is well behaved, it should cache that for a day.
Okay.
Now, if they did a restart or something, then you would expect to see a repeat.
Right.
Or if they're not caching it, you'd
So
expect.
it could be that a few percent of the repeats are,
Okay.
you know, okay.
Yeah.
Okay.
Right. That's,